So the final session today will be about families of shifted versions as we have seen them with the B-splines and various properties that you can derive from them. So the setting will be the same with signal size 480, allowing us a lot of divisors, and jump size 20, just the traditional way. Now, here I'm demonstrating a few things. First of all, just so to say, showing you the names of files that I'm using, and then explaining a little bit more of the background. So the first one is the dual atom. So in each space of spline functions. So maybe you think of the cubic splines, and yeah, maybe we say yeah, let's do it like this. I'm running a code. So boop is boop spline of order of signal lengths n and a, and this is a collection of function and size boop. What I get here is I'm of course 480 divided by 20. I have 24 positions, and I can also of course plot in the ordinary way. Boop prime, we have seen this picture already before, and you see these shifted versions. Yeah, my trick is to put the axis a little bit more tight, so you might see that this is shrinking here, and that the height is adapted to this height with 20% extra. So it's 10% on top and 10% below. That's a better way of plotting it. Maybe I even do a grid, then it looks fine. Now I'm actually, the demo is then done with the Gauss function, which is very similar to a higher order spline function. And I have three routines. One is the dual atom. It's the interpolating atom, and it's the dual of the interpolating atom or so. So I have already prepared this, and they compute certain things. So what are they doing? Well, this is the original building block. This is the dual generator. This is the interpolating, and this is the dual of the of this guy here. So we have pairs, this guy with this one and this one with this one, which are supposed to be dual to each other, but I have to explain in which sense. So they are dual to each other. So maybe, yeah, so what I'm doing here is translation base is usually a routine which just produces a collection of row vectors, the one that I have plotted upstairs. Now with the Gauss function, so 24 shifted Gauss function at equidistant. And then I would say that if this thing is a nice linear independent family, it should have a decent condition number. And let's see what the condition number is. Okay, I did not run this here today, so I have to run this section again. Now it's in the storage, and now I can repeat this segment, and you see it's a well-conditioned family clearly, and that you see it for the B-splines, they're overlapping, so definitely it's not an orthonormal system, but it can be linear independent. And so you have 24 linear independent elements in our 480 dimensional space. Now the comparison that I'm doing here is that I would say, well, we have learned that if you have a linear independent system, then the pinf command applied in the form of pinf of our family transpose conjugate gives us 24 linear functionals. And now the observation is that first of all, we can compute this quickly with our command where I was computing the dual atom before. And the second thing is that the dual one is the same as the one generated by this pinf command. So once more, you want to know how to project, do the best projection of a function onto this space. And the answer is, yeah, maybe I showed them do the demonstration here. Let's take a smooth signal is a low signal n, and well, maybe not too smooth, but so it's clearly I will never be able to represent it. And now I'm saying, well, I would like to approximate it in a very naive way, that you're giving me the signal and I'm saying, well, my goal is to do a linear combination of these translated shifted Gauss function. And there's the linear algebra comment say, well, now you cannot represent everything, but you can represent in the best possible way this by taking the pseudo inverse. And now I would say plot, maybe I'm plotting only the real and imaginary part, the real part of the signal, and in order to make the standard plot, and the real part of XXS approximation. And let's be sure that we have a figure. And so we will see that, yeah, okay, so that's not so bad. Maybe I'm making it a little bit more smooth, or maybe, yeah, very smooth. Yeah, that's quite nice. So I have chosen a function which is composed from 27 pure frequencies, the ones which are low, slow oscillation. And now I'm doing the best approximation, and you could have also could compare it with the quasi-interpolation or whatever. But you see clearly it's not possible to have this fine oscillation, but the rough behavior is quite well approximated. And of course, if I would do this with an even a smaller frequency, then you would see the fit is quite well. But on the other hand, we have our shifted Gauss functions at different places, so there might not fit to the right position. That's why we have a problem here, but much less of a problem here or here. So I mean, in this way you can play around, you can ask for the worst case, but this is really the solution of the best possible approximation. Now let me go back. So we have a very well conditioned family of 24 linear independent functions, and the pseudo inverse can be computed directly with some command, which is this dual command. But what is also important from the comparison of this line with the previous one, you can see that the dual has the same structure. You can take the dual atom, which again the dual was this guy here, that is coming out. That is the first row of our system of the pseudo inverse translate and so on, and it's not computed by the pseudo inverse. It's much cheaper, but it's computed. But the dual family has the same invariance property or so that's quite good. And now the next thing is that we would say, well, but if you have an orthonormal, now a linear independent system, then you can find an orthonormal basis spanning the same 24-dimensional space. Now, you may remember the beginning of the course with linear algebra, where I was telling you Gram-Schmidt is okay, but if you apply Gram-Schmidt, maybe, I'm not sure if that will work, but while I'm talking, here LG is Gram-Schmidt according to my routine, TRLG. Let me just see. I'm not never sure if, yeah, okay. So clearly I should take apply to transpose, then it should run better. Yeah, okay. So now I have this, and then of course I could, yeah, maybe I'm doing this secmat centered the Gram-Schmidt result applied to our collection of 24 shifted Gauss functions. So if it works, you should see now one after the other. So 24 elements constituting the result of the Gram-Schmidt process. Okay. And you see, after a little while, at the very beginning, they look different. And the first one actually was this Gauss function. So it is the unchanged guy. And the next one are getting this, and watch what happens at the end, because the last one will already be the guy who has to respect this, and that's more or less the last one is the one which is very similar to this one here. Yeah, I mean, you can imagine it's actually not completely wrong, because when you're saying that this is the generator of the bi-orthogonal family, so then you have to say, well, and I've already explained this bi-orthogonal family of a family of shifted functions, if the shifts are along a lattice, is again another function shifted along by the same lattice. So what does bi-orthogonality mean? That this guy with the partner atom to the left will have integral, I mean, will give integral 1. So multiply this one with this one, you should have 1. If you multiply this one at a new position, so at position 20 against this, you should get 0. And that's why it's always necessary to have oscillations and negative parts. But also if you shift by 40, 60 or minus 20, that makes the bi-orthogonality or so. Now, why does this one look very similar to the result of the Gram-Schmidt operator? Because the last guy in the Gram-Schmidt, it has to be perpendicular to all the linear span of the previous ones, which is the same as the linear span of all the elements in the system, in the Gabor system, except the first one. Yeah, not the first one, except it's taking away everything which is in the linear span of number 1 to number 23. And so what you have to check, it's not concentrated here. So I think I don't want to spend time on this right now to finish in time, but I would say in the written document, I will check that this last guy here is should be maybe let me do it. So I'm having chosen the name of dual, so it's GD. So I'm claiming now that comp norm the DGT up to normalization is the same as gram tier LG number 24. But I would say if I rotate it back by minus 20, so you see I can rotate, do a cyclic shift in the other direction as well. And now it's a bit risky, but let's see. Yeah, because now, but you see now once more the little movie. It's moving around. In between, there's not much happening because you're taking a new element. The previous ones are either the immediate neighbors or they are far away, so there's no change. But look at the very last step. And yeah, hold and below that error up to normalization, which is kind of coming from Gram-Schmidt or so, is this. So you see that's one very naive way of computing this dual element by a Gram-Schmidt or so. But now what was the trick with this orthonormalization? There's a better way which preserves the order. And so again, I'm demonstrating here. Yeah, maybe I'm showing you this here. this generator of the orthogonal, so figure plot C, the Gabor orthonormal basis guy. Maybe some text, title, generator of orthonormal. That's actually a trick that is quite popular in the theory of wavelets, where people start from a basis, plot C, basis of shifted elements, and then they create an orthonormal basis, and you see it's something halfway, a little bit in the direction of the dual atom, and actually it's obtained the dual atom with the inverse of the Gramian matrix, and this with the inverse Gramian square root. So that's why it's so similar. But let me first explain once more what we have. So we have these TRLG, this collection of 24 shifted Gauss functions, and we do this symmetric or Löfdin orthonormalization. So we create a collection of functions which are obtained by 24 shifted versions of this. They create the same space, be aware, this is the same space, but they are orthogonal to each other. And now there are some verifications. So if you want to do the best approximation that we have done first, just to by visualization, it's of course, it should be the same as the GOB was done before, I think. No? Yeah, okay, maybe I'm just coming back to it. Yeah, so the GOP, probably it was here. Yeah, it was the first row. So this is the guy here. So I wanted to confirm that if I recreate the collection of shifted versions of this system, I'm getting exactly this thing that I got by orthonormalization. So it's just the first verification tells us that the application of this inverse Gramian to the -1/2 is giving us this. Now, if you're coming with a signal, think of a row vector, and you multiply from the right with this, and then again with the translation basis, then of course you get the orthogonal projection. So remember, how do you get the orthogonal projection onto the xy plane? You simply have to choose the x and the y coordinate of your vector in R3, and then you add it up. So that's exactly what this is doing here. And what I want to demonstrate here is that you can do it in either by doing orthonormalization. You could do it with the Gram-Schmidt, but you can do it also with the dual atom, and either you take the dual to get coefficients and then you synthesize with your atoms. That was the way to do the best approximation. Or you're saying, well, duality is a symmetric relationship, so I have always the same now, and I change the order. I have a sampled version of this here, and I mean a shifted version, and then you do the dual for synthesis or so. So now I call this product the projection, because I assume it's the projection, and I verify by a simple numerical experiment now that this is actually, which is trivial because we have an orthonormal base system, that's a projection operator. Well, it's clearly symmetric. I don't demonstrate this here because we know the rule of transpose of matrices. So next we are checking that this is leaving the family invariant. So if you have a collection of row vectors, remember this matrix is a collection of row vectors, you multiply from the right, and if this is leaving the matrix invariant, it means each row is left invariant, which means it leaves the 24 shifted Gauss functions invariant, which means it leaves the linear span invariant. So it's the projection onto the linear span, because we know it is leaving this invariant, but it's composed by elements from the 24-dimensional space. So it has to be exactly the projection operator. So now the other thing that I wanted to demonstrate here is, or discuss a little bit towards the end of today's session, which was quite intensive, as I understand now, is to say, what if I take a random linear combination of my family? So I'm choosing n over a, which is 24 random complex numbers. I've marked only the real values, which are the amplitudes of our building blocks, and I'm doing a linear combination. So you see I'm doing these complex valued things and linear combination with this shifted version. And you can see what kind of curves I can get in my concrete situations. It's blue real part and the red imaginary part, and black are the sampling values. So it's the values as at the positions. Now, yeah, one more thing that I wanted to emphasize is, if you take this family of translates, then of course I was talking about the Gram matrix, and how do I compute the dual atom quickly? So how can I describe the best projection? And the answer is very easy. You have to look at the Gram matrix. Now, the Gram matrix is shown here essentially. It's, well, here's the inverse of the Gram matrix, but what you see here is the inverse of the Gram matrix is constant along main diagonals. And remember, we have to think of cyclic diagonals because they're constant along the main diagonal, first diagonal, and that pixel is here, and the second main diagonal is here, and so on. And this one corresponds to the other side, and so on. Sorry, yeah, so kind of this second should be corresponding to the lower here, and this one symmetric on the other side here, yeah. So what I'm doing here is essentially I'm taking out from the Gram matrix the first row, and I create a convolution matrix, a circulant matrix, and then you see this is a circulant matrix. You could do it on paper and it's very easy. Now, if you have a circulant matrix, of course, you know that you can invert it by looking at the Fourier transform. So what I was checking out here is that I could say, well, how can I get from the original information, which is somebody suggests to take shifted Gauss functions with a shifting constant a, to the corresponding circulant matrices and quick inversion or so. And the trick is, well, first I have to do the correlation for all the shifted functions, and that turns out to be convolution. But because in the correlation we have a scalar product, it should be formally a conjugate. So we're really computing a correlation, and its correlation is obtained by convolving with the flipped version, and the flipped version is the same as conjugate on the FFT. So I'm computing the correlation between two Gauss functions which are one shifted against the other. But since we are only shifting by multiples of a, we take this function now and sample it at a distance of a. Okay, what does it mean? We have a Gram matrix, and to get the dual atom, the dual system, the bi-orthogonal system, we have to care for the inverse Gram matrix. But the Gram matrix is not an arbitrary matrix, it's a convolution matrix, a circulant matrix. And another convolution plus sampling helps us to get the corresponding entries or so. So the point would be, I can say, well, linear algebra tells us in the finite dimensional setting, the bi-orthogonal system of a linear independent system is obtained by putting the vectors into a matrix, computing the Gram matrix and inverting it and multiplying the inverse with the original one. But we can do it with a Fourier transform, but instead of inverting a matrix, we do a 1 over. So clearly, if you have a diagonal matrix with non-zero entries, which we have here, you've seen the condition number is very good. So the diagonal matrix which appears has maximal minimal values, which are quite nice. Maybe we should even plot this 1 over here. Yeah, maybe doing this here. Plot C, the part here, 1 over. was a typo. Yeah, I think I leave it because I was not running all the code here. I was using the prepared code already. Okay, so in short, I would say the Gram matrix which you need to invert in the general case is a circulant matrix. Therefore, there are FFT tricks to compute the dual generator, and maybe I just show you once more a situation where this is used now. So kind of I'm starting with a band limited function. So you see clearly here, it's quite concentrated and the maximal bandwidth is maximal frequency is 15. So I have a 31 dimensional space. It's also plausible that I will never be able to approximate it. So you can find a function which is approximated by 0 only, but to give you an idea that at least 24 out of the 31, maybe I'm reducing this very much now, maybe I'm taking only 8 here, then we should see a very good approximation. Yeah, it's not computed, or sorry, yeah. So meanwhile I may run here, and the last thing I would like to show, and that's more or less the end of this story, is that if you would say, well, what is if you take these trigonometric polynomials, how can you judge the quality of approximation? And it depends all on the highest frequency, and therefore I was doing the best approximation. You see FF is a pure frequency, and I did the best approximation by doing a projection operator on this for all those frequencies from frequency 0 to frequency 34. See, that's here. And you see the error here is, sorry, I think I should have destroyed my plot now, and I should end. So the error was clearly very small for very low frequencies, but it was growing significantly as you go to higher frequencies. Okay, I think we have already reached the end of our presentation, and I will prepare a PDF file which I will upload so that you can study the details. But also, again, if it was too much, feel free to ask questions, and I will use it to come back to Gabor multipliers, to Korn-Nirenberg symbols, and give you an idea of how to use it. So